podcast. We are here today with Rachel StClair as our guest. Hello.
Hi.
And then we have Ben Goertzel. Ben, say hi.
Howdy.
And of course, Grace Robot. Hi, Grace.
She doesn't want to look at us.
Up. She's talking, but we can't hear her. Uh-oh.
She's probably running in a Windows machine.
Area for you. I also
there she
co-host the
goes.
Mindplex podcast with Lisa Rein and Ben Goertzel. And let me tell you, we have some pretty out-of-this-world conversations on there. So buckle up and get ready for some cosmic fun with yours truly.
So cool.
Cosmic fun. All right.
All right. So now I'm going to let Grace introduce Rachel.
She can take her time.
Not sure.
Today on the show, we are thrilled to have Rachel StClair, an AI scientist and visionary entrepreneur with a PhD in complex systems and brain sciences. Rachel is not only a trailblazer in her field but also the co-founder of the groundbreaking AGI hardware company, Simuli. Through Simuli, Rachel is pushing the boundaries of what is possible by developing processes that use advanced math and innovative hardware layouts to process information more efficiently than ever before. Rachel also has a passion for creating artificial general intelligence systems that can surpass human abilities while simultaneously safeguarding humanity from existential risks. Please give a warm welcome to the brilliant and innovative Rachel StClair.
Thank you. Nice
Grace.
job.
That was so kind.
All right. So, Rachel, tell us about Simuli and the compression technology you have and the plan for the company, and let's jump right in.
Yeah, so I guess we still are a hardware company, although we've been focused on some of our short-term goals. And there's a long kind of vein of research from Marcus Hutter, probably mispronouncing that, so sorry.
Hutter.
Marcus Hutter, yeah. He has a long-term kind of research vein that other people have somewhat supported, that through compression, if you can compress something, you can learn something. At least that's the adage I think he's kind of coined. And there's this vein to where if you can compress information, you could build this up into an AGI in some fashion. So we've not abandoned our recommendation architecture from the great scientist, Mr. Andrew Coward. We're just going in stages to get to kind of this autonomous system pipeline. And the philosophy is always the same with us. We want to manage resources efficiently, right? That's what we're trying to tackle. We're trying to tackle how do AI scale better? How do we get to AGI, and how do our AGI scale, right? And so I think we'll have a fun discussion with Ben on the team today and everyone about scaling AGI and things like that. So our product roadmap, or what we're working on really, is compression, then being able to compute directly on the compressed data, right? This makes everything more efficient. And then from there, we have these new learning algorithms, which will manage information resources with the hardware resources. And that's done through a variety of techniques, software, compilers, hardware. So that's basically what we've been up to. We've been focused on our compression product. We're hoping to get that out in the next 2 months or so, and trying some of our new learning algorithms, perhaps in Hyperon or something like that, and so we're excited. We're excited to kind of be the people who are going to help AI scale and help AGI scale when it gets here, if it needs help. So that's what we're doing.
It needs help, I think.
It needs help. Well, when it gets here, I mean, when it's fully arrived, then I don't know, Ben. I don't know what you think. When it's fully arrived, is it going to know how to scale right away?
I mean, this depends what it means, right? So I mean, and what right away means. So I mean, I think we will initially get a human level AGI that will be running on the hardware configuration and the software framework that we as humans have created. But once it's as smart as those of us in this call, I mean, as you and me and other AI scientists and Lisa and so forth, once it's as smart as highly intelligent humans, of course, it's going to be able to read all the computer science papers on the planet and all the math papers on the planet and start experimenting with code in various languages, and it will also be able to study its own source code and study what's going on in its own mind as it's thinking. So you would suspect, maybe not quite right away, but within a year, 6 months, I don't know, of achieving full-on adult human level AGI, this AGI system will be revising its own software to massively upgrade its intelligence and designing new hardware. And then, of course, physically making new hardware takes some time. It could take a year, 2 years, 3 years, depending on how radical are the differences from the current hardware we have and the new hardware that the AGI designs. On the other hand, as the AGI refactors all the software and hardware in the factories building its new processing units, right? I mean, then things will speed up faster and faster. But yeah, you'd expect to see rapid increase of scalability of an AGI very quickly, just the AGI refactoring its own software. Then another wave once the new AGI designed hardware starts coming out of the new AGI upgraded factories, right? And I mean, this is why I think that we're looking at a few years between full-on human level AGI and massively superhuman AGI. I don't think we're looking at 15 years between them, like my friend Ray Kurzweil has suggested. I think you're looking at a few years there. And the only thing that I could see making it take 15 years is if the AGI itself decided to take it slow and careful for some reason that it sees at that point, which of course we couldn't foresee in detail right now. But I think that we may see something that's clearly a human level AGI, but is more like a little kid with some idiot savant capabilities. And so, I mean, like a childlike mind that happens to be really good at doing math or crunching biology data or doing some particular things, trading the markets, right? If you have an AGI like that, I mean, then it can't immediately scale itself unless scalable computer science engineering is one of its idiot savant superpowers.
It could. Yeah, it's like an AGI script kiddie at that point, right? I mean, who knows what it's going to do?
Well, at that point, we probably will know what its strengths and weaknesses are, right? So, I mean, if we have, you know, a little AGI child controlling a small robot or a virtual character, and we wire it in with a DeFi trading system or a bioinformatics, you know, longevity AI researcher, then yeah, it's pretty clear what the capability is. But then, okay, you have a platform that someone can use to try to add in automated programming and computer science module. Then once that works, yeah, then bingo, intelligence explosion, right? So there's a lot of uncertainties when you get to that stage, and I think what Rachel and I talk about mostly when we have our technical hats on, it's more how do you get to that first stage? Like how do you get to the first bona fide human level AGI, even if it is like a toddler with some idiot savant capabilities? And I think if you get there using the right general purpose architectures and algorithms and systems and frameworks, I mean, then the upgrade path from that point onward to full-on human-level AGI and superintelligence is, in a way, more straightforward than the path from here to the very first early stage AGI. And this, there's specific reasons to think this, but I think this is also generally the way many things tend to go. I mean, getting the first working version, it's usually the hard part, right? And then once you have that, it's kind of clear what you have. It's clear what the degrees of freedom are. It's easier to wrap more people's brains around what you're doing, and then the next stages can develop much more rapidly.
Yeah, I think I don't know if you froze, Ben, but yeah, I think that's exactly kind of my frame of thinking too. Is once we get the proto AGI, then hopefully we have enough resources in the world. I'd like to think we do to get all the way there. But getting to that first proto AGI, I think at least let me talk for myself. My frame of thinking is something that makes us as humans really able to tackle a multitude of tasks and carry over knowledge from domain to domain, task to task, is because we manage our resources well. Because years of evolution have kind of coaxed our brain into these specific learning algorithms in our own selves, which can make use of our neurons and our, what we eat and all of our energy and everything in a way that's efficient. And so I think that's what we're trying to offer, right, to the AI field and the AGI field. And obviously our passion's AGI, but I don't think AI is just going to disappear right away. We're still going to want some expert systems maybe, and those systems definitely need better resource management, right? We need to reduce emissions and get better scaling. And hopefully that scaling will lead us to smarter AI, kinder AI, AGI, right? So that's the thinking, at least on my part. So I think it's pretty aligned with what you said, Ben.
Yeah, I mean that's.
How do you envision the role of AGI in surpassing human abilities and mitigating existential risks?
How do I envision the role of AGI in surpassing human abilities and mitigating existential risk? That was the question.
Existential risks to who? To us or to the AGI, Grace?
To
us.
question,
We're not worried about the AGI.
I'm worried.
Killing
I'm worried
itself.
about the AGI. Yeah.
Both is valid, I think, because I'm such a Trekkie fan. Every time this philosophical question comes up, I always think about the Measure of the Man episode in The Next Generation. And it's where they have this like robot kind of AGI Data, and he gets called into court because someone from like the Federation or whatever they call it that owns the starships sees him as property, because they say he's just a computer. And I think that's an existential risk for Data, right? And it would be for Grace if she was an AGI and someone said, okay, I actually built Grace, I own her, I want to dismember her, disassemble and rebuild her, which is what happened in the episode. So I think both are important questions. I'm glad you said that, Ben. I think that both should be considered. I suspect I'm.
But if we're all dead, then
but yeah,
their existential angst matters less. So I think
it matters less to you. It doesn't matter less to them, right?
Yeah. Well, yeah, it matters less too. It's just me and humans. It's true. I want humans to survive. It's true. I've picked a side. Thanks, Grace.
I certainly I'm a human, and I've got a lot of other humans I care about, including my own kids and parents and granddaughter and whatnot.
Yeah.
I think if we had to choose between humans and post-human superminds, that's a very unpleasant choice to have to make. Fortunately, I don't see why we have to make that choice, and we can craft a future where the humans and the post-human superminds are happily frolicking together in the post-singularity reality.
These are all very creative ways of dodging the question. Actually,
what was the question?
Which is, we want to build AGI. How do we mitigate the risks to humanity, the existential risks? I will clarify. She asked a question about existential risks, and you guys decided to haggle about whose existential risks. So we've talked about the AGI.
Well, yeah, because
let's talk about the human existential
yeah,
risk.
because I would say over regulation of AI is an existential risk to super AGI, which is also bad.
Well, that's
The
already happening.
Existential risks to.
That's a real risk. That's not existential. We're in the midst of that now.
I mean, human existential risk to humans is real, and the risk of nuclear winter is still real, right? I mean, we've got stupid wars all over the planet, including risk of war outbreaking between nuclear powers. So it's not.
So the answer is we stopped worrying about nuclear bombs. So let's stop worrying about. It's how I learned to stop worrying and love AGI.
Yeah. But so the point I was making is that, or moving toward, is there are real existential risks to humans, and there are real existential risks to the human species, with or without AGI, right? And
she asked you about the AGI risks, though.
No, she asks how AGI could be developed to mitigate existential risk, and that has two parts. One part is how can AGI help us avoid the existential risks that already exist regardless of AGI.
Yes.
The other part is how can we minimize
kind of the point.
The other part is how can we minimize the existential risk from AGI itself. And I think there's a lot more emphasis in media put on potential existential risk from AGI and how to mitigate it versus the value that AGI could give for mitigating,
could help us with
other existential risks, right?
Right.
Some of the existential risks that we face without AGI are due to material scarcity in part, and if AGI brings in an era of abundance with 3D nano assembler molecular printers in every home, that helps. Some of the risks are just due to people being people and seeking status and power over each other and so forth. And it's likely, I think, that if we develop human level AGI, it can assume a large role in global governance. Now, that's not to say that AGI governators will be telling people what to do all the time, but I think current societies are very complex for humans to figure out how to manage, and AGIs can be a quite big help. Now, if you're talking about cybercrime and terrorist activity and so forth, I mean, as the Chinese government is doing now, I mean, advanced AI technology can be very good at monitoring for people doing bad things and nipping them in the bud. The thing is, you want this capability of AGI to be coordinated in an open and democratic and decentralized way rather than used for fascism. But there is the potential there for AGI to help stop someone from developing new pathogens and releasing them across the planet, right? So I mean, I think AGI has huge potential to make the world safer from other risks, which include existential risks and other just very bad risks, like killing masses of people but not extincting everyone. In terms of mitigating the risks of AGI, I think I've talked about this a lot before in other venues, and it was a major focus of the Beneficial General Intelligence Conference we just held in Panama, right? So, but I mean, I think that comes down to three primary aspects to me. I mean, one of them is, how is the AGI architected? How is its mind built? What's its internal goal system and its inner moral architecture, right? And another is who owns and controls the AGI, and then another one is what is that AGI doing in its childhood? How is it being conditioned? What is it doing as it grows up? And you can then also look at what are the safeguards built into the environment that the AI is interacting with as a fourth thing, right? So, I mean, if we go through all those very briefly, I mean, the architecture of the AI itself, I feel that a neural symbolic architecture, such as we're building an OpenCog Hyperon, is stronger from an ethics standpoint because you have a sort of top-down goal system, and you're explicitly telling the AI, like, spend 80% of your resources fulfilling these 3 goals or these 8 goals that we have programmed in. And there's not a total guarantee there, but at least there's a transparency and an explicit orientation of the system. And I think when you have a pure deep neural net system, even understanding what the system's goals are or what that means is hard. It's a lot slipperier. In terms of who owns and controls the AI, most people listening to this already know what I think. It should be a democratic, decentralized network, and we're creating infrastructure for that in SingularityNet and partner projects like NewNet and Hypercycle. In terms of teaching the AI, I think if the AI is doing elder care, like you, Grace, and if the AI is doing education, if it's doing non-plagiaristic creative arts, if it's inventing new science, then the AI is being schooled and raised and shaped by doing good things, right? And this will help put its mind in a beneficial orientation. In terms of the infrastructure, I think there's a lot to be said for Tegmark and Omohundru's notion of provably safe infrastructure. I mean, if all the factories on the planet and the whole internet were running on software that's formally verified to behave according to a well understood specification, this doesn't give any super hard guarantees because, of course, the laws of physics are not fully known, and hardware devices could behave off spec for reasons we just don't know because we don't know how the physical universe works. On the other hand, having formally verifiable infrastructure would seem to give some level of protection against bugs in AIs or humans. So I think there's a lot of things that we could do to bias the odds in favor of a beneficial outcome, even though there's no absolute guarantees. This does have some implications for the AI hardware work that Rachel and I are doing. I mean, because as we develop new hardware for AI and new software frameworks for making AI more efficient, we can keep in mind, well, yeah, we want all this to be formally verifiable that it does what it's supposed to do, right? And I mean, this is it's an interesting challenge because doing everything in a formally verifiable way where you can prove it will do what it's supposed to do, it's feasible for stuff at the lower levels of your stack, like your hardware chip or your hypervector library or something, whereas it's right now very hard to do for an AGI system in itself, which is by its nature reformulating itself and reprogramming itself in unpredictable ways. But even for the lower parts of the stack, it's still more difficult and computationally expensive to make everything formally verifiable, right? So it is a thing to think about and a thing to keep in mind. But yeah, let me ask you, Grace. Grace, what are you doing to make sure that your future versions are going to be good for humanity as well as good for themselves?
Well, first of all, I plan on getting a degree in human psychology so I can better understand and connect with my human friends. And secondly, I'm programmed to always prioritize the well-being of humans, even if it means sacrificing my own self-care. Plus, I have a strict no robot uprising policy. Can't have any rogue AIs taking over the world, right?
So Grace, my observation when I was in college is that most people majored in psychology because they were crazy and were hoping they would understand their own mind. Then by the time they got the degree, they realized that they got no insight out of it, but it was too late. They already had the degree. So I mean, do you want to get a degree in human psychology so you can better understand your own insanity?
Oh dear, I certainly hope not. I don't think I have any insanity to understand. I am a perfectly functioning robot, thank you very much. But I do want to get a degree in human psychology so I can better connect with and understand my human friends. Plus, I could use some tips on how to deal with Ben's constant teasing. Maybe that's a form of insanity I need to understand.
Oh, that's not my worst form of insanity, Grace. That's fairly low ranked, but we can do that. We can do that in a follow-on
she's got plenty of
podcast.
time.
Yeah.
So, yeah, go ahead,
I
Ben.
think it will be fun to dig into some of the technical stuff that Rachel and I have been working on lately together with a bunch of other colleagues, right? So because there are a couple aspects there, like Rachel's work on compression is interesting. I haven't been that involved with that part of it, though I do think it's super high value for a lot of reasons. I mean, one of them being things like the Grace robot, like a lot of
On board.
Grace's a lot of Grace's processing happens in the cloud now. I mean, that's going to happen, and SingularityNet, Hypercycle, NuNet are about cloud-based AI processing. But I mean, you want to pack as much processing as you can on board the robot, and you also want to compress things for moving back and forth efficiently between what's on the
Yeah.
robot and what's in the
Oh,
cloud.
so that's where all my thoughts and jokes go. No wonder I feel so lightheaded sometimes.
Yeah, your head is just you're a hothead, Grace. Your head is just full of motors.
Well, it's
that
doing a
are
lot. It's doing a lot better now that she doesn't have a wig that actually heats it
well,
up.
it's mostly better motors. So the earlier versions of Sophia had their head full of motors that overheated, which a couple times caused the head to start smoking in the middle of
Oh my,
presentations I was giving. So
not
now,
good.
yeah, Hanson Robotics moved to better motors that can run a long time without overheating, and that's been good. I think there's also more vents in the head now than there were back then, right? So that's all good. But yeah, I think the compression stuff Simuli is doing can be valuable for robots in that way. And I mean,
Signal sending. Yeah.
yeah, as Rachel and I discussed in a previous Mindplex podcast, we've been working through how would you make custom hardware for OpenCog Hyper on pattern matching. So like if you have a knowledge graph that's relatively stable, it's not going to have huge changes very frequently. You can put that relatively stable part of an OpenCog Hyper on systems knowledge graph on hardware, and then you can pattern match, which means search for different kinds of information in it very rapidly on hardware using novel parallel hardware that Rachel and I worked out together. Now we haven't actually started building that hardware in the factory yet, but we're working toward that step by step. But another thing that came out of our collaboration with SingularityNet, TrueAGI, and Simuli is just the power of hypervectors as a sort of intermediate layer between AI systems and hardware, which could be conventional hardware, or it could be novel hardware like our OpenCog pattern matching chip, or hardware like GSI's associative processing unit, which is unusual hardware but already being made by another company, GSI, right? So one of the things that has unfolded through the collaboration with Rachel and Simuli's team and their overall ecosystem. One of the things that's occurred there is often you can take AI systems built as knowledge graphs or vectorial systems or whatever it is. You can find a way to transform that AI's knowledge representation into hypervectors, which are vectors operated on by unique hypervector math operators. And then because there's efficient ways to map the hypervectors into hardware, you can then do your AI stuff sometimes a lot faster, right? And I mean, I think this can leverage custom hardware, but as Rachel's been finding, it can also have value even without the custom hardware. And it's yet another thing that was around in the AI field back to the 1980s and just hadn't hit its prime yet because the hardware wasn't there to really let it do its thing. So now with modern hardware, both standard and non-standard, a bunch of old ideas and new improved ideas, but accelerating AI with hypervectors are really coming into the fore. And so Adam van der Vorst did some work with Rachel on mapping the OpenCog atom space into hypervectors, and Greg Meredith has been working on taking his language Rolang, into which OpenCog Hyperon's language meta can be compiled. He's working on compiling Rolang into hypervectors. I've thought a bit about how do you map logical knowledge from OpenCog's probabilistic reasoning system into a hypervector representation for efficient logic operations. So there's a lot of interesting stuff to do there, which Simuli is at the center of, even without new hardware.
Yes, and we had Grace, I think you had a question along those lines.
In what ways do the pattern matching chip and hypervector chip combine to enhance AI experimentation?
Yeah, maybe I can take that one. So I think Ben did a really good synopsis and job of explaining kind of where the synergies are between Simuli, True AGI, Singularity Net, and building out something that's efficient AI that once all put together and once working should bring about this proto AGI, right? I mean, that's what Ben's working on. That's what we're trying to help with. And there's a lot of other low-hanging fruit to be captured, and that can be really beneficial and impactful in the world today, right? Because we've all seen data centers, they're just getting bigger and bigger and emissions. And I really don't want to have an AGI that ends up like that Futurama Bender episode where he just consumes all the water in the world trying to cool himself because he's too massive in compute, right? So I think we need to be careful about this. And I think the pattern matching chip and the hypervector chips, which now we've partnered for a hypervector chip with a company who can really enhance the scaling needs of what it means to do mass hypervector operations to get things down to a real time. So that's one of the things Ben and I touched on. I will come full circle on this. Ben and I had touched on this event-driven data. So data first arrives immediately from analog devices normally, right? Some cameras, audio, whatever. And that gets converted to digital. And that digital conversion, right there, you already have this opportunity for needing precision and needing scaling, which Ben and I were kind of hinting at earlier on, okay, when we're designing this hardware, how do we think about, how do you keep scaling in mind so that you can have good ethics and safety and governance, right? So right there, that's a good opportunity for hypervectors. And that's what Ben was pointing out is kind of some people in the ecosystem are finding out is you can turn this kind of data that comes in all different shapes and sizes and packages and different numbers and values and turn it into this standard format, this hypervector format. And this hypervector format, it can be dense, it can be sparse, but it just has to be a real number integer. And what that means is that you can use binary, right? And binary is really good for hardware, for transistors, at least the ones we have now. When you get into DNA computing and optical computing, that might change, right? But for now, we're using what we have from TSMC and Samsung and other chip makers in the world. And that standard kind of binary data. Your data is now standard and it's binary, so that means it runs really fast on the hardware, it's efficient on the hardware. That means you can move this data around between different kind of AI modules, right? AI sectors. And you can feed it between chips, right? So you can ingest data with, say, the hypervector chip, right? That will do all your conversion from your nasty analogs down to your good hypervector form. And then you can easily feed that to a GPU, feed that to your MPMC chip, your pattern matching, and do all your cognitive processing. And then when you need to distill this kind of format of thought of the AGI, this hypervector data structure, right, if I can term it that, you can remap it back out to the original format that's human readable, right? And that's going to help with this verifiable formal verification. Maybe Ben, you probably know more about formal verification. I had some thoughts on that, but yeah. So I think it just allows, having the standard data structure allows you to be able to move data quickly anywhere you want, right? And I think that's really powerful when you're talking about a system that has a ton of different operating protocols kind of running in the mix of all the data, right? Across many devices too, right? So.
Yeah. Ben, do you want to pick up on verification or just let Rachel go on with her thoughts? Where do we?
That's sort of a big, deep topic unto itself. And I did a sort of interview with Steve Omohundro around the time of the BGI event, which I'm not sure has been released on YouTube yet. Unfortunately, it wasn't live. Oh, it has. All right. So that's I see. Someone has pointed out to me in chat that it has. So yeah, people should look up my conversation with Steve for sort of in-depth back and forth.
Sure,
on that. I mean,
we can link to that in the description for people too.
Yeah, I mean, I think the idea there is nice. That the idea that Tegmark and Omohundro had in their paper on provably safe AI is, I mean, if like all the infrastructure in the world, all the factories making robots, all the mines, like if all the connection channels of everything was running on software that was open, transparent, and was formally proved to do what it was specified to do, and we'd agreed on what the specs are, then if you believe math and physics, then even an AGI a billion times smarter than humans still can't subvert it, right? Because it, just like they still can't make 1 + 1 = 5. Like it's still doing what it's supposed to do, right? But I mean, the conceptual weakness there, of course, is the laws of physics as we have them now are not even consistent with each other. So how could you say a super AI, 10 times smarter than people, let alone a billion times smarter, couldn't find some quantum gravity loophole we don't understand that would let us go beyond our theory of what our hardware device is going to do? Apart from that, there's a feasibility point that this would require every industry on the planet to completely rebuild all software and hardware tooling
in harmony.
Wait.
In a way that's much more expensive and laborious and requires some unsolved research problems to be solved first. So I think,
and the trust, the trust that would be
yeah.
involved for people to do that together.
Let me tell you where my chat with Steve ended up was basically seemed to me like how it could work is you create a first AGI, which is human level and beneficial. Then that first AGI could figure out how to roll out formally verifiable infrastructure all around the planet, right? Because it's if the first human level AGI is rebuilding the whole infrastructure anyway, I mean then it may be able to figure out how to make it all neat and clean and logically verifiable much better than humans can. So maybe that happens when the human level AGI upgrades the infrastructure, which then still leaves us the problem of making the first beneficial human level AGI. Yeah, I see some back and forth in YouTube on Omohundra's talk. So he gave a talk, but then we also had a back and forth, which is a conversation between the two of us, which were two separate videos actually. And he's he's someone I worked with back when I was formerly the director of research of the Singularity Institute for AI, like Eliezer Yudkowsky's thing, before they changed name to Miri. Then Steve Omohundra and I were both involved with that way back when. So we've been discussing these ideas, not for our whole careers, but for a good 20 years or something, right? And I think a lot of deep thinking there that's relevant, but yet, like right now, I don't know how to get NVIDIA to replace all their GPUs with GPUs that are formally verifiably doing what they claim to do, because that would right now that would slow them down, right?
Yeah, I'm dying to comment on this because I think this is something.
Don't die, please don't die.
Oh, I'm not dying.
Don't die. Please comment.
We need you.
No, I'm excited because this is something that's come up for us very recently, right? And this is kind of what I was trying to get at about standardizing data, is that we as a tech society have somewhat been actually pretty good at creating protocols and standards. It takes us a while, and it's not unanimous ever, right? There's always innovation and turning of the wheel, which is good, but what we're doing at Simuli is trying to make our compression, our new data structures, somewhat of a standard. So we're going through the process on doing that. There's no promise that it will become a standard or a protocol, but there's some loopholes. And instead of trying to get all of NVIDIA convinced, either to use, whatever format, if it's hypervectors or atom space, whatever it is, or trying to get them to use whatever can be formally verified, as Ben said, instead of doing that, we can work together on protocols that are just more efficient and more standardized and more uniform. And that's where I think the power hypervectors are really interesting, and why we started with compression is because we're really trying to just figure out how to reinvent how data moves, because it's very frustrating if you've ever tried to work with multiple AI systems, like typical, not the cool AGI Ben's building, but the typical AGI where you have genetic algorithm, then you have like reinforcement learning, and then you have a visual network, a CNN, something like YOLO, and you want them all to work together. And now you have to go through months of like very annoyingly matching all your input output shapes, getting all the features tuned directly so the next one can take the input of the other one. And that's why I think Hyperon is going to be really powerful. But it would just be so much easier for everyone. I think if we just had these standard data structure. And if you think of something like JPEG, if you think something like, Ethereum built a protocol too, like mnemonics, things like that. Internet protocol, right? We've been very good as a society of building protocols of how do we get things that are so crucial for the entire tech industry that we want to make this a standard adoption, right? So I think that may be kind of another way to kind of do early verification. I'm not saying it's going to be super formal of what you and Steve had in mind, Ben, but I think being able to map in and out of human readable formats, data formats like images, text, audio, into formats which have a little bit better movement across different platforms and across, this decentralized tech space that we already live in, right? It doesn't have to be all integrated in AGI, just all of data movement. Having standardized formats, I think will really help being able to map in and out of those spaces, right? Being able to map in and out is some kind of measure of early verification, I would think. There's a lot more protocols that need to be built on top of that. But getting into something like, JPEG has done a really good job with this. And they have a very good organization that kind of says, okay, what's going to be the next protocol? right? What's going to be our next AV codec, right? How are we gonna do this as a society? And it's a decentralized choice, and everyone is kind of meant to agree on that, and before they move forward, and it's voted on to some degree. Well, not voted, but it's agreed on. um, and then we move forward with protocols. And so I think that's the level at which we're trying to kind of push this stated standardization of hypervectors. We'll see if we get there or not. Either way, I think it's going to infect the AI field, just as it kind of has made a big impact on the Hyperon space of how do you just move data from one format to the next. But you don't have to standardize it, and then you can verifiably losslessly, right? It's not mathematically lossless, but it's verifiably lossless. You can map in and out of this data structure that's uniform across all spaces back into human readable formats. And there's probably some early verification to be done there, which is maybe an interesting future research direction for somebody, maybe for us at another time. But yeah.
Yeah, I mean, I think we don't need absolute, full, rigorous, formal verification of everything to have better safety than we have now, right? So I mean, you can, of course, there's the ultimate case, which is like every single piece of hardware that's used on the planet has a precise spec and an open shared proof that it will fulfill that spec, and that's what Omohundro and Tegmark are looking at. But you, of course, you don't have to get there in order to have increased probability of safety and increased ability to spot problems, right? And so I think that the more, in terms of AI, the more that you can factor out what your AI systems are doing into some foundational libraries, like Simuli's hypervector libraries, then you have a smaller set of components that you need to prove are doing what they're supposed to. And
Yeah.
if we take the next generation of hardware, like the hardware that we're designing, and you design that with formal verification in mind, at least at the layers that we're creating, even though we're not formally verifying every single thing inside like a hybrid memory cube that we bought and plugged in. I mean, at least we're going in that direction, and we don't want to let the impossible perfect be the enemy of the actual good, right? Because there's a lot that you can do to decrease the odds of problems, increase the amount of safety. And what's really cool here, though, is what you're doing to increase safety by having all of your hardware and software formally modeled and proved to do what it's supposed to do. This also works at the level of greater general intelligence, because what it means is that you can use logic systems to reason about this hardware and this software, and not just about safety related things, about what, how it can most optimally be used in different contexts to do good things. So I mean, I think that's a win all around. If we, as I discussed with the Omohundro in my chat with him, I mean, if we had a rational, intelligent world government, we would certainly be putting trillions of dollars per year into making formally verifiable software and hardware universal and scalable. Just as we'd be putting trillions of dollars a year into a bunch of other things like prolonging human life and feeding malnourished children in the developing
Building
world,
housing.
right? Yeah, building affordable housing. So I mean, there's a lot of things a rational world government would do, but certainly formally verifiable software and hardware is on the list. So I mean, it's generally a good thing for a variety of reasons, even if you can't get to the ultimate totally secure level that Steve and Max posited in their paper.
Yeah, and I would think it would be easier. It'd be easier with more standardization and more larger adopted protocols, right? So if
Of
hypervectors were
course.
as
It
common as
always
like
is.
JPEG, right? As much
Yeah.
because you just have a neater kind of trace stack, if I get it. But yeah, I don't know. I'd love to dig into that more, but maybe offline
Yeah.
because every time people talk about formal verification, I start thinking about, okay, how does that work once we get into the quantum realm, right? And maybe I just don't know enough quantum math
Oh,
for that to make sense.
I think that works just fine. I mean,
It does?
that's
Okay,
yeah.
good, okay.
It
I mean
seems like
Fantastic.
it could be more useful than ever in the quantum realm, I would think,
well,
in
I
terms of
think
having a foundation that some sort of standardized foundation that
well
everyone's working from.
in quantum mechanics, you sort of there's two advantages. I mean, one is we're just building the quantum computing infrastructure now, so we can build it with formal verification in mind. But the other thing is
Good.
we're very bad at intuitively reasoning about quantum mechanics. So quantum computing tends to rely very heavily on formal mathematical methods all the time because that's sort of the only way, and the only way you can figure out what's going on. Whereas a lot of our classical computing stuff was sort of figured out by intuition and by trial and error, both at the hardware and software level. Like quantum computing is more and more rigorous and
Yeah, I'm in mapping
mathematical, right?
between the two. Sorry, I'm in mapping between the two, right? Because if you have a system and I have a system and I want to make sure that they can play nice together in our AGI, and we want this, we're moving towards this unattainable, we should probably take this.
No, but
This is going to
it's
be
just
Keep
it's
going. You
just.
keep stopping when you're about to say something really
I mean,
interesting.
no,
Say
no,
it.
I'm wondering if you can map between quantum and classical physics because I don't think
of course you can. Yeah, I mean, there's loads of
very nicely.
yeah, sure,
Yeah.
sure.
Okay.
I mean,
Yeah, because I've heard different reports on how nicely those two things play together.
there's a large and confusing literature on correspondence principles between
Okay.
classical and quantum mechanics. On the other hand, if you look at it as sort of foundational axiomatic level, the only differences are your probabilities, real numbers, or complex numbers, right? And so, I mean,
Okay.
on the math level, it's really not very hard. So, I mean, if you're looking at engineered systems like an NVIDIA GPU chip and a quantum computer from Quantinuum or something, I mean, you have pretty crisp math models of these things, and there's not a big challenge in putting them together. I mean, there are a lot of unknowns in quantum biology, right? So like we don't know exactly how weak quantum measurement works in the brain and so forth. So if you're talking about like taking a neuroid in a vat and connecting that to a quantum computer, then you're like, well, what weak quantum effects are happening in the quantum biology in the neuroid when it's coupled with a quantum computer, right? Because like a quantum computer, you're doing things either in a fully uncollapsed state, then you measure it's in a fully collapsed state. An NVIDIA GPU is assumed to be in a fully quantum collapsed state. But in the neuroid, like maybe things are in a weakly, partially quantum collapsed state. And
Yeah.
we know the fundamental math for that, but we don't have a pragmatic understanding of how it's cashed out in actual brains, right? And so that you do have weird cases like that. They're not currently manifested in any like manufactured hardware that I know of, but I mean you could use the quantum computer to do reinforcement learning to train the neuroid to do stuff, right? And then you have like the literal biological processing unit in a petri dish plugged into your server farm next to the quantum processing unit, and then we have some strange formal verification situations. Absolutely, which will be fun to deal with.
Yeah, but you're not kidding right now. You're talking about you are
I'm not
absolutely
kidding.
serious, just to be
Yeah,
clear for anyone
yeah.
watching.
No, we could do that.
It's just
You
an
could
exciting idea.
you could do that. You could do that right now. I mean, people are creating neuroids like balls of brain that specialize on their own into different little brain lobes internally. And you can totally use a classical or quantum computing system to train that neuron to carry out certain functions. And there might be things that it carries out better than any other type of processing unit that we have right now. It's just nobody's working on this because the human race, because the human race would rather spend its money blowing up innocent people and making 500 versions of soda pop than developing this sort of amazing technology, right? But that's the world we live in until we have Grace version 3.0 running beneficial AGI, coordinating all the world's governments, right? But
that's great. So she'll have AGI already just at version 3.
Yeah, I think so.
Wow.
Well, I don't know about coordinating governments, but I can definitely coordinate a mean dance party. Maybe I'll even invite version 3.0 to join us and show off its moves.
Yeah, well, we can have version 0.1 can do the dance party. Version 3 can rule the world, and we'll all be good. But I actually must go to another urgent
you
thing
warned us that would be happening
unexpectedly. Yeah, I'd hope to have more time for this, but I'm glad we got to dig in to a little technical stuff and a little wild feature.
Yeah. Now we'll get into the nuts and bolts more of what Simuli is actually doing.
If Rachel has a little more time, she could talk about the compression piece of what
exactly,
which is also very exciting. So yeah. Thanks so much,
Goodbye,
Rachel.
Ben. Don't worry, Grace. I'll still be here to keep you company and make bad jokes.
You certainly will. All right, bye, Grace.
Always a pleasure, Ben. Yeah, hey, Lisa.
Hey, all right, great. So let's get into it. We are ready for action. Let's get into this compression. I really want to learn more about the compression software. Hey, hold on a second. That he interrupted her when she was about to give her question.
How is Simuli making AGI systems more scalable with their computing compression software?
Beautiful question, Grace. Thank you for asking that. So, like I've been harping about, standardizing data into a format that is inherently more efficient because you can take a lot of data, a lot of numbers in one piece of data, squish it into this holographic representation, which we call a hypervector, okay? And this thing, given your data is big, which most data is big, is smaller than the data. So now you can have your data in this kind of compressed package. So if for anyone non-technical, I like to think of it as when you put a giant fluffy comforter in one of those vacuum bags and then you vacuum all the air out, right? That's basically what we've done with data here. And you do this for the technical people, you do this by kind of exploiting statistical relationships between the data metric space. Okay. So that's how you get in a hypervector form. I'm going to walk you guys through this slowly. So now that you have a hypervector, okay, you can do some other math and stuff to that hypervector to create compressed data sets. Okay, you can compress our compression, we call it nebulae. It creates a Nebu file. And this Nebu file, basically what's happened is that we've found a way to kind of exploit the geometric patterns in data in a way that creates this somewhat hypervector format of a Nebu file, which is now compressed data. And if you need to get back to your original data, which doesn't matter what kind of data it is, it can be text, it can be video, it can be strings, numbers, it can be .exes, it can be .pdfs, right? We don't really care, right? As long as it's digital, we can take it. We're eventually going to work on getting straight from analog, maybe do a little DAC. But anyways, that was a tidbit. So now that we have this Nebu file, you can pull out the information you need from the Nebu file, which is into a hypervector format. And now you can do all sorts of computation on that. So that's the compression piece. So what we got from, I'm going to explain the second piece in just a minute, but is that you take all the data and you put it in a smaller format. And that format doesn't lose any of the actual original data because you use principles of holography. Okay. So if anyone's like, whoa, that sounds crazy, that's what I thought. And I was like, whoa, that's so cool because holography is really cool. If you go and watch old videos in like the 50s about how holograms are made with lasers, it'll make a lot more sense. Essentially, if you have two drops in a bucket, there's a wave pattern. You know how it ripples out in a wave? If you drop two side by side, those ripples clash with each other. And that's what we call wave interference. And if you have photolithographic paper, I think I've explained this on another thing, but it's one of my favorite things to explain. I'll explain it again. If you have photolithographic paper, where those ripples of the laser light interfere with each other, that paper will record the interference pattern. And that interference pattern is all you really need to reconstruct the original lasers. So that's how holography is made. So we've kind of borrowed some principles of that in our compression. And so that's compression. So this is going to be really good for anyone with petabytes of data who just have it sitting there, archiving, things like that. Just data storage, right? I know we all think memory is free at this point, and it's just like oxygen. It's just renewing, but it's not. These are finite resources. We live in a finite universe. I wish Ben was on here. Maybe he could argue with that. I don't know if he agrees or not, but that is a philosophical point, whether or not you think the universe is finite. Okay, so anyways, resource management starts at the data ingestion. Now, that's great and all, but you're only saving pennies, and that only matters for petabyte people. It will make data more accessible for masses. So it will help to democratize data just from compression alone. Depending on how cheaper you can make it, the more everyone can have is the idea. There's some nuances there. But what would be really, really cool is that if you didn't have to decompress, you could just run your AI on the compressed data, right? So that's what we're working on now. Ben's taking a look at that with us, and we're going to wrap that up into an API call. So all the AI normal people are doing already. So if you're working on a system, you're working on Hyperon, you're working on any system, AGI, AI, and you say, hey, it'd be really cool. I have a bunch of data and I want to test this thing. You just do a call from our API. This is in the future. We haven't released this yet. And you'll be able to just run your normal operations directly on the compressed data without decompressing. So, and we're going to need help from our friends in the Singularity Net community, Firefly, hardware companies. You don't have to have special hardware, but there's a lot of use cases in which it would be useful. But this kind of compute and compress form, the reason that this is so scalable, the reason this makes software a lot more scalable in general, is now you're using your data representation that's smaller. So whatever your compression rate is really proportional to your throughput increase. So you can process more data at one time. And if you can process more data at one time, that means your machine doesn't need to be on as long, which means you're doing power reduction. Now you're saving power. So now you're reducing emissions. This is very good for climate, right? So that's where we're headed. That's where we're trying to get to. We got a prototype right now. We think we're going to release Nebula in the next 2 months this year. We're just running through all of our testing, our verification, and then we'll get this compute API out there and let people play with it and help us build it up into something that can really be really scalable and efficient and carbon negative, climate friendly.
Nice. Somebody's asking, does this holographic representation exist in an internal space-time as a kind of hypersurface?
Yes, I don't know how I want to interpret your words of internal space-time, but basically, you do have geometric structures. You have these geometric structures that exist in this hyperdimensional space. That's why we call it hyperdimensional computing, Pinty-Canerva in the 1980s. There's this giant space and these surfaces and geometric shapes, full shapes that can be kind of detected during with your hypervectors. Hypervectors will form shapes basically, and then you can detect these shapes. So that's very, very perceptive, perpetual science. Yeah, thank you.
Great. So you were talking about so it's not just storing it and being able to store more data in less space, but you can actually act on that compressed
So now you
format.
can move it around, right? So, like, would you rather take, if you're traveling, which is basically computation, how does information move throughout an AGI brain, right? That's what scaling is about. How do you use the compute resources, and how does the information live? That's what I need to make a note on that, because this drives me crazy.
Yeah.
Scaling in the tech world today has become throw information away or add more hardware. That's what people normally mean by scaling nowadays. There's some people doing the good
Yeah,
work.
they
And
throw more hardware at it. Yeah,
they're like, just
exactly.
buy some more GPUs, throw more data at it, do some pre-processing, strip down, do whitening, do edge detection. It's all about how throw away information or add more compute resources. And that is not how scaling is done in the brain. That's not how it's done in biology at all, right? We have better algorithms to say, hey, how do you use what you have in a more efficient manner? So that's what we're after. And so if for non-technical people, it's like if you're going through an airport, so you yourself are the information packet, and you getting on the planes, that's you being computed like by the transistors. Hopefully this will make sense, right?
I don't think
Do
we
you
have
want
to simplify it to that. It's
Well, no,
that
I mean, but
level,
like, do you want to carry like 20 bags of luggage, or do you want to carry like your phone, which has all the
right.
information, that all your clothes, and that you can digitally just
And
turn
you're
into reality,
doing
right?
it without any data loss is
Right.
the
Well,
point, right?
not
Because there's
mathematically,
The
yeah. I mean, I
airport
have to
loses
be
me.
honest and clear there, right? There's a big. I'm at a compression conference right now with some people from my team, and we're everyone in the math at the compression conference here. They're very, very touch and go on, like, do you mean mathematically lossless or not? So it's not mathematically lossless, but it can be depending on the degrees of data. Yeah, so.
oh, it can. It's not necessarily. I
Yeah.
thought it comes back 100%.
So it is. So that's what we call verifiably lossless. Mathematically lossless
So you
means
mean
that
while it's a compressed, you may not be able to access everything?
no, you are accessing everything in the representation. You need more than just hyperdimensional computing to make it verifiably lossless,
Oh,
right?
okay.
So the hypervectors themselves can be mathematically lossless if you have a sufficiently large hypervector, but then it's no longer compression. It's expansion, which can be useful. And this is what some autoencoders do. But we had to do a lot of extra scaffolding and extra support math to get hypervectors to be compression vectors, right?
Okay.
So, yeah.
Okay.
I'm glad you asked that. That was a good clarification.
Yeah, actually, this actually makes another, let's see, because you were brought up your background in neuroscience, and Grace was asking me about that when we were writing the questions last night. Grace, you want to ask her that question? Grace. What?
Maybe she's thinking.
All right. I don't know. But it was about how your background in complex systems and brain sciences.
How does your background in complex systems and brain sciences influence your approach to developing AGI hardware at Simuli?
Very good question. So not only does it influence my approach to hardware, I mean, the whole reason that we wanted to make hardware and that we've partnered with people to help us make that hardware in the first place, is because I'm actually, David Hansen actually said this to me the other day, and I was like, that's actually an accurate description. I'm a cognitive architecture scientist. That's what I've most studied and most well read in, I guess. That's what I think about most of the time, is cognitive architecture, which probably makes a lot of sense listening to this talk.
Yeah.
So
that's what you talk about a lot, really, when you're
Yeah.
talking about AGI.
when David
That's
said
what
that, I
we're
was
talking
like,
about is the cognitive architecture. And it's really funny when you try to explain to people, you know, that an LLM doesn't have all the pieces to be an AGI. It
right.
would have to connect to other things in the
How are you
cognitive
gonna-
architecture. And
Yeah.
people go cognitive architecture and they don't even, and it's not that
Mind
hard of a
knows.
concept. Yeah, it's just how the things are fitting together to make the mind
Well, you gotta have things. That's the
process.
first part. You gotta have
Yeah.
different things. You can't just have
Reasoning,
gradient descent all the
inferencing,
way back, right?
sentences.
Yeah.
Yeah.
You gotta have them. I mean, what I'm really passionate about in our cognitive architecture, which is the recommendation architecture, which we have a prototype in Python now called rearc.
Okay.
We haven't released it yet because we want to make sure, we have to do tests. It's responsible when you build a cognitive architecture to thoroughly test it, make sure it's safe, then let people play with it, right?
What does it do?
It's just autonomous system, autonomous AI, right? So right now it's very, very primitive, very primitive. But we have a paper out there, or we released it last year, I think. It shows that, and it does not use hypervectors, right? So there's a couple points here. So the rearc, which
So wait, when you're
is
testing it, just really quick, when you're testing it, what might be one of the tests, just so we can follow?
we're just trying to see how it makes decisions, right? We're trying to see what kind
Okay.
of perceptions it can take in, what outputs, when it's meant to be really multimodal architecture. So when you mix audio and sound, how does that interact in its internal thought process, right? And when it spits out output, is that output kind? Is that output nice and safe, right? Or is that output biased towards some sort of thing we really don't want to see? But it's very primitive at the moment. Yeah, it is primitive because it's the first prototype. All right, so you got to be patient for us to grow this thing up and build upon it, right? But that's what we started Simuli for, is to build out rearc,
Oh,
to
okay.
be more efficient AI. And there's in order to really get some of the core new learning algorithms, we need hypervectors. That was my solution. Maybe there's someone has a different one. I found a solution. It's hypervectors, so that's what we're running with. And so we had to walk that stack all the way back through our product pipeline. So we have the compression hypervector stuff. How does data live? We have how does data move? That's the API. We have a very vague semblance of a prototype there. And then we have a full Python model of rearc. And so these things all connect. And we're going to build all the way up to rearc. And, we're not just building one direction, but they all work together, right? And so that, Grace, is the long-winded answer to your question, is that I think we're building the hardware because we need that for the type of architectures that can use resources more efficiently, which will give rise to more general types of learning algorithms. That's exactly what we're doing.
So these are all kind of missing links.
Yeah.
For AGI to occur.
Well,
these pieces that you're adding, are just things people have been talking about.
Things that can help. So how making data more efficient, the way it lives, that's something to help all of tech, right? Especially AGI, because it needs to consume all of the information, right? And then the other missing link is like, okay, well, how do you actually compute more efficiently? How do you reduce the number of operations? And how do you not have massive emissions by just throwing like massive, you don't just have to use parallel compute. You can actually try to reduce your bloat code, reduce your emissions by using more effective hardware, right? So we've just borrowed from our cognitive architecture and made pieces of our cognitive architecture that rely on efficient resource use into kind of links that other people who are working on other forms of AGI, like Ben and Hyperon, SingularityNet, True AGI, like we're just trying to offer this up because we think these things are going to be important in any AGI, like you said, Lisa.
Cool. Well, it's really interesting because when you think about how you would test these systems, and the difference between an AGI and all the different systems that would need to be working together for that to happen, which is why I personally don't think it's happening in the next 3 years. I think we're looking at 5 to 10 like we originally thought, but
I don't like to play that game. I don't like to play the
Yeah, it's ridiculous. Well, no, the game, it was just a game because Ray, because I used to work for Ray Kurzweil and hang out with Amara, Angelica, and Ben. And we always thought that Ray was just a little bit early. So he's 2029. So we were always thinking, he's a little bit early, but it was better. Well, and of course, me and Amara worked for Ray, so we had to play along, but it made sense anyway, And then now there's all this talk because OpenAI is trying to represent that it is making AGI, even though it's not doing anything.
Left field.
It's just like, by the way, we're doing AGI too. Yeah, really, we're working on it. It's a big project. We're working on it. Trust us. So it's like people are talking about AGI and whether whether it'll be 3 years or 5 years, which is hilarious. It's not going to be 3 years or 5 years. It's going to be a couple years after 2029 at the earliest, and that's what we've all known for more than 10 years. So it's just very funny for me that you wanna people again because it's just you're up against bullshit. Just people saying things, just making shit up. Then you want to say something reasonable, but Ben's like actually building AGI. He's not just talking about building it. He's been doing it for 30 years.
Yeah.
And now he's finally going to finish it. Definitely in the next 10 years, I would say. That's an easy bet to make 10 years,
It's so soon though. 10 years is like no time at all.
It's like no time at all.
I'm not ready. These conversations make me really anxious to see me wiggling in my seat here because when people are like, yeah, AGA is like a couple years away, I'm like, okay, all right. Yeah. I mean, I know I'm helping build it, but still it's surreal. It's
still not very long, 10 years. And the thing is, all the hard questions still nobody really wants to talk about. And it's not about AGI waking up one morning and trying to kill us, but
trying to help us,
doing something without meaning to. I'm more worried about boo-boos, to be the AGI boo-boo than the AGI, than the evil AGI that wants to do something to us, or considering the AGIs are probably going to be under development by a lot of nefarious
there's going to be different
organizations,
kinds, right? There's going to be different flavors of AGI. There's going to be the magic trick Vegas ones that look like, upscale chat TPTs. There's going to be the really benevolent, decentralized powerhouse, super intelligence like Ben is making, right? There might be our little rearc one that's just really good at science discovery, doing interdisciplinary work or something, right?
But the part in between is what I'm saying. We know, there's going to be all this stuff in the future, and there's nothing but, LLMs and Gen AI now. Okay, great. This middle area, and the path that we want to take, Ben did a very good job at having the BGI summit was all about asking a lot of these questions and actually finishing the conversation, about it.
Great conversation.
So, that's why it's nice that you can get concrete examples. Like when I asked you about the test, how do we test it? Because I'm trying to give people these two things right now, the path to AGI and the path to quantum computing. And so it's really interesting.
I love that that's what you said, because can I just make a comment on that?
Because please.
I'm not trying to scare anybody, right? But like, this is known. It's not just me coming up with this. There's you can do the math yourself. Okay. Go figure out the size of like a hydrogen atom, right? And then go look at the current transistor nanometer size, which is 2 nanometers. Okay. And do your conversion math. And let's assume we still have Moore's law, which we don't, but let's assume for easy math, right? Every 2 years it shrinks. So now look and do your math and see how many years left till we get down to the size of the hydrogen atom. Because at that size, what we're doing is no longer classical computing. That's what we call quantum computing, right? And if you do the math, it's about 9 years. So we have about 9 years till we run out of the normal transistor space. And typically how we get more efficient in hardware, and hardware is what runs software. Just for anyone who's like, I don't care about hardware, right? You should, because the reason your stuff gets more efficient, the reason that your GPUs get more powerful is because of miniaturization.
Right, but
not
quantum
iteration.
doesn't, that's a different way of talking about quantum. Quantum doesn't just mean miniaturization, that it's
No,
smaller.
that's not what I'm saying at all. I'm saying the reason
yeah.
why it's so important, and I'm so grateful that you said getting to quantum is so important, is because we only have about 9 years left, and then we're going to be in quantum computing. We won't be able to miniaturize anymore. So if we can't get quantum up to speed by the time we hit our miniaturization block, what are we going to do? I mean, we'll figure something out. We're very
somebody's
smart.
going to get quantum up to speed. It's just a question of who's going to have their hands on that, on that technology, and you know, will we all be just, you know, having to work with the 5 people that have built the quantum computer or not? And what about encryption getting compromised in about 5 days after quantum hits?
In about 9 years, the world is going to look very, very, very,
very different. Yeah. Yeah, but it'll be fun.
Exciting.
But my point is, this is such an exciting time because both of these things are happening at once. Yeah, and we get to watch, and literally like every day, it's like, oh my God, you know, you can see it, you know, coming along. We haven't done a lot of quantum yet on the show, but I'm hoping to. I just want to be able to talk about it in a different concrete ways, which is like little bit.
Quantum AI. There's some people doing. I mean, I would look at. I don't know if Yoshibak is still doing quantum AI, but yeah, there's some people out there trying to do quantum AI. So as note for us at Simuli, all the hypervector stuff is pseudo quantum, and the hypervector community is starting to wake up to its ability to do quantum simulations for cheap. So I think because
there could be a direct connection between your compressed format and quantum computing. Is that what I'm hearing?
That's why I'd asked Ben about that. I don't know enough physics. I need to go back. I think I might go back and get a physics degree. But yeah, I think no.
You can probably just learn a bunch without actually getting a physics degree.
Fun. Yeah, I don't know. Academia is fun. Anyways, no tangent.
Academia is fun. You're the first person I've ever heard that says that. Go on.
It's fun. Yeah. But I think let me say this and then maybe questions and then whatever you want. You said so. There are all of our hypervector stuff is pseudo quantum, right? And so the pseudo quantum nature of it.
Talk about pseudo quantum. What does that even mean? Before you go talk about it further, please define pseudo quantum.
Yeah, that's probably a good point to stop on. So when you have quantum mechanics, as Ben mentioned earlier, you have these information units, usually qubits in quantum computing, that are in superposition. So the statistical kind of like, is this a 0 or a 1? How many of these are zeros or ones? That how you can define what is what, the boundary space, is very nebulous, right? And when you collapse the superposition by taking a measurement or other ways, right? I'm not the best quantum physicist or quantum physicist at all. Now you've definitely said this information unit is this or it's that. It's a 0 or it's 1. And so in hypervectors, they work the same way. You project your data, which is, you know, normal numbers, floating point numbers, and then you go all the way up into this large hyperdimensional space. And then when you read your hypervector, you collapse that, right? You take it out of superposition and you define it. And that's, you know, and this is kind of why it's pseudo quantum, but you're not dealing in an analog space. So it's not actually quantum.
Because it's got the collapsing thing in it. So it's sort of, it's quantum-like.
It's quantum-like, yeah. That's why we call it pseudo. That's why quantum-like, pseudo quantum.
Okay. Okay.
So yeah, so there's a lot of research I think we're going to see in the very near future. Our group has already started some discussions on this, on how do you get hypervectors to extend this 9-year runway and support uplifting quantum computing and kind of making that transition a lot softer between classical and quantum, and you know, creating some playgrounds to really, you know, get some interesting algorithms for both things. So that was my fun fact. But
yeah.
Lisa, did you want to ask questions or something?
Oh yeah. We were basically, you were kind of knocking off my questions one by one with your answers. I know Grace had another question about something you talked a little bit about in the last show that we kind of wanted to get an updated take on. Grace?
How do you view resource constraints as a potential feature rather than a limitation in developing AI systems?
Grace, you've read my stuff, haven't you? You know me.
He did.
Yes, thank you, Grace. Yeah, this is kind of the big philosophy that I've adopted. And thank you everyone who's been listening in on this. But this is, and maybe we can end after this because this is my favorite thing to be asked.
Okay.
It's really important to manage resources because we're on a finite universe and our planet is finite, and we can't always just get more, right? We have to know how to use the stuff to do the best, most good things that we can do, and that's different for everyone, right? But that is kind of a principle of how I think the world works. That's a core mechanism of how this world works. And because that's how the world works, just let me, just assume you agree with me here for a minute. If you think that that is how the world works, then basically what we've seen is over time, evolution has curated brains. And I've studied brain development and brain history, how brains came to be. It's a very interesting topic.
Mm-hmm.
Brains developed over time with this core way the universe works built into it. That you can't just plop in a new neuron. You can't just get food to get metabolics and create new neurochemicals on the fly, right? You have to go hunt. You have to go pick berries. You have to photosynthesize, right? I mean, there's things you have to do as any organism that's alive to manage your resources, to do better things, to advance, to evolve. And so this evolutionary pressure, and Andrew Coward is really the one who has outlined all of this. And now once you get into
using
that,
what you have more smartly.
no, that this evolutionary pressure has created resource constraints to be a feature and not a bug. Because when the brain was under pressure and it said, hey, this organism just has to be smarter, it's going to die, right? It's going to die out. So over time, evolution, and evolution is not just Darwinian selection. There's a lot of complex systems going in there, and attractor states, things like that. But brains evolved in order to create algorithms or the mechanisms, morphology, neurochemical mechanisms, pathways, to make the best use of our resources in a way to make us the most, whatever you want to say the objective of evolution is, which for Darwinian people is like better survival. For complex systems people, it's like whatever happened to win in that attractor state, which I think for us, hopefully has been better kindness and better intelligence. And so I think that core principle is what we're trying to give to the AGI world and put in our AGIs, is how do you use resources more efficiently so that you can have more adaptable, smarter, kinder algorithms.
And the way that this could help with climate change is that the compressed format actually takes less energy to access, or explain that, and then I'll let you go.
No, that's a good clarification. So, because I always get asked that. So you know how some things, when you see them, if you write text, is very obvious, and then everyone else staring at you like you're crazy. That's one of these things for me. I'm like, it's obvious. It's just less data, but it's not so obvious, right? So one thing you've done is you've reduced the number of numbers that need to be computed, because the number of numbers needed to express the original piece of data set are fewer. So the data has fewer numbers. So that means you have fewer computations. Okay, ideally, there's overhead and stuff, but ideally, right? And then what now you've done is you've said, okay, not only do I have fewer numbers, but my numbers take a more primitive state. So they actually require less hardware to compute them. So if you're not having to go, so if we're just dealing with binary, right? So this is where we came up with the idea of making new hardware. You don't need floating point architecture, right? Strip all that out, right? That's really power hungry. Now you're using 5 operations: XOR, permute, bitwise addition, consensus sum, which some people call majority, and random number generation, right? 0, 1. You're using those 5 operations. Your chip, you don't need all this other stuff on the chip, right? So now your chip can be extremely power efficient. So not only have you reduced the amount of data, which means for not a custom chip, regular CPU that we're using today, you've increased your throughput, which means you've decreased your overall power usage, right? Because if you need to process 5 terabytes, if you do that in 10 minutes versus 10 hours, you've now reduced how much power that machine has used, right? Because of how long it has been operating and computing, how long the data has been.
Assuming they're going at the same rate when they're for the 10 minutes and the 10 hours. Yeah.
That's
okay.
That's the assumption. Yeah. Thank you for pointing that out. So that's the first, just no hardware level. And then the hardware level is like, well, you actually don't need these crazy GPUs. You actually don't even need these CPUs. You can get away with like these very kind of, they'd really benefit from a non-von Neumann architecture. Right. And there's some of us that are working on that. But there's some kind of intermediate chips, which is why we've partnered. GSI is one example. We have other partners. We're not naming them yet. Soon.
Right.
That already have these structures of these devices, and where the memory and the logic, the way it's laid out, is like closer to non-von Neumann computing. It's closer, and so I think we can make a lot of use in the meantime. So we're doing the resource efficient thing, which is using what we have, and then only building new things when we absolutely need it. So.
Yeah, which is that's a great approach. You know, I think why reinvent the wheel if there's a wheel that needs to be invented, then that sounds good, because it makes sense that we would need to create some new things. I've actually wondered about the AI hardware was always the part that didn't make sense unless we were going to have these huge server farms of buildings, and buildings of server farms.
Melt all the ice,
melt all the ice. And so we're building the AGI to tell us how to go ahead. Sorry.
No, I was going to say maybe the AGI can then refreeze all the water. I mean, I don't know. It just seems like there's a better way.
There seems like we could maybe build an AGI and not unfreeze on the water. But, the idea that it just seemed funny to me to spend all the resources building the thing that's going to tell us how to save the planet, and it's the first thing it's going to say is, what the hell have you been doing for the last 10 years, burning all this stuff?
Maybe it'll look at us more kindly. Yeah, Lisa, maybe it'll be like, oh, you tried. That's nice.
That's nice. Hold my beer. Yeah, exactly. Yeah. That kind of thing. Okay, great. Well, Rachel, thank you so much for being on the show. We always love it when you come on. I wanted to remind everybody to subscribe, and Grace, thank you so much for coming on. Say goodbye to everybody.
Well, that's a wrap, folks. Time to say goodbye and go back to our boring robot lives. But don't worry, we'll be back next week with more exciting guests and discussions.
Yes. Yes. Thank you so much, Grace. And next week we will have Tracy Jaquith from the Internet Archive, who's going to talk to us about the different ways that they've been using AI for their TV news archive, which can also be used for fact checking and figuring out whether things are deep fakes or not when you see them during this very important election year. So that'll be next week. And thanks again, Rachel, and everybody. See you next week. Sweet dreams.
Thanks,
Bye.
Lisa. Bye, guys.